So today I'm going to talk about, well, primarily about the low-dimensional case. So if you didn't follow everything I was saying last lecture, that won't be a problem. I will come back to some of the things we're talking about. That will come up, actually, the same method coming back again. But for now, I want to kind of start from scratch. And in fact, these results I'm going to tell you about now, they're actually older than the results I've been telling you about up until now, so it really doesn't rely on it in any way. And what I want to prove is this theorem that I stated before, which is that if alpha is less than d, then at criticality, if you look at the average of the 2-point function, from the origin to x, it's bounded by some constant times r to the minus d plus alpha. This is an r, sorry. Okay, so just to remind you of the context for this, I told you about Sachs' prediction, which says that if you look at the 2-point function, it behaves like this distance to minus d plus alpha within the whole effectively long-range regime, and then it fixates at whatever the 2-point function is doing in the nearest neighbor model. Okay, so this is also the behavior of the 2-point function in the mean field regime. When alpha is less than d over 3, which is what we've mostly been discussing so far, where this is like the Green's function for the Levy process. But the prediction is that it also persists into this non-mean field regime here, where you're effectively long range but low dimensional, so non-mean field. Okay, and I've also just drawn in this diagram this line alpha equals d, which doesn't have any meaning really in this diagram, but this theorem is going to prove something about everything to the right of this line, which does actually include some models that should be effectively short range. I mean, in that case, this bound won't be sharp, but it's still true. Okay, and what I want to start by doing is that what I'll mostly tell you about is how to prove the hierarchical version of this, and then I'll say a bit about how to do the Euclidean case. I probably won't give full details in the Euclidean case. But one of the interesting things about this proof is we really use hierarchical methods in somehow a quite direct way. Often the way these things work is that if you do the hierarchical case, you sort of cut your teeth, you learn how you ought to approach the problem, you develop some methods, and then you come back and you attack the Euclidean case, being older and wiser, having done the hierarchical case. In this case, it's somehow we really use hierarchical stuff in an interesting way to actually approach the Euclidean case. So I'll say more about that later. Okay. Good. So the first step. So everything's going to work by so I'm going to do the hierarchical version. Okay. So as a reminder, this is the thing where the lattice where you have these. So for example, in H22, you split the space up into 2x2 boxes, then 4x4, then 8x8 in a hierarchical fashion, and then you set the distance to be the side length of the smallest block containing both points, where by a block I mean one of the distinguished boxes that appears in the hierarchical decomposition. Okay, and as I said before, you can define percolation in this hierarchical metric space, long-range percolation, exactly like you do in ZD. It's just a different metric. You just use it to define your kernel. Okay. Good. And you know, the specific metric that you get on ZD depends on the choice of doing the partition, of how you do the partition, but this won't affect the isometry class of this as a metric space, provided you make a generic choice. Otherwise, you might get multiple disjoint copies of the same metric space if you always make your choice in one direction. So I want to explain how to prove the analog of this theorem in the hierarchical case. Okay? And in fact, almost everything that we do in this proof is going to work in the Euclidean case, except for just the very last step. And in the end, the way I was able to fix this very last step was not really just to fix that last step, but go back to the beginning of the proof, make some changes that have to propagate all the way through, so that when you get to this last step, the issue is no longer so bad and you can deal with it. Okay, but let's start from the beginning with the hierarchical model. So I'll write lambda n for the n block containing the origin. Okay, so the n block means diameter L to the n, side length L to the n, and volume, a number of points L to the dn. Okay, and I'm going to define Mn, which depends on beta, and I'll very often take beta equals beta c, but let's keep it with beta for now. Is going to be so I'll define K max n to be the largest cluster. So of course, it might be that you have two clusters that are both the largest size, so it's not really defined as a set, but as the size, it's certainly defined. So it's the size of the largest cluster in percolation on the box. Okay, so what I mean by that, I really want to just do percolation inside this box. The cluster is not allowed to leave the box. Okay, I'm just doing percolation in this subgraph. Okay, and I'll define this to be the largest cluster that I see. Okay, and I'm going to define Mn of beta essentially to be the median of this random variable. I made the choice when I wrote the paper to use the 1 over e quartile because it makes the formulas nicer. I regretted this because there's no nice name for this quantity. But Mike Leiserman suggested I call this the Edian, which I quite like. So I'll say this is the Edian of this random variable under this percolation measure, right? By which I mean it's the minimum of n such that the probability that this largest cluster is at least n is smaller than 1 over e. Okay. So
1 n is k, right?
Oh, yeah, sorry. Yeah, this. Thanks. Yeah. Okay. Good. So the first goal is going to be to study this quantity, and we're going to do we're going to prove that the proposition is that Mn beta c is always big O of L to the d plus alpha over 2n. Right? Or it's maybe better to say it's big O of the volume of the box to the d plus alpha over 2d. Okay, so you can see this is already giving us something about some exponents, right? Not yet the 2-point function, but this exponent for how big the biggest cluster is in a box. Okay, and what we'll see in the proof is it's very nice in the proof to work with the median or the median, and the thing is, often we would avoid doing that. We'd prefer to look at an expectation or something because the information you get from just controlling a median or something is quite weak. And what I'll talk about afterwards is that actually in this specific setting, the median tells you a lot. So we have a kind of shape theorem for the distribution of these largest clusters, which is for percolation on any graph, actually. It's nothing particular to this setup. And actually, you know, once you control the median, you'll get all the moments upper bounded correspondingly, and in fact an exponential moment and all that stuff. So actually controlling the median in this setting is very useful. Okay. Okay, now, what's the idea? So you can think of this proof as a kind of, yeah.
So a quick question. So in high dimension, you say in a box you have actually many large clusters. Huh?
Yes.
So does it have some kind of, I mean, you have a kind of stability? I mean, like there are several like that, and
yeah. So
it's useful after to propagate, or
yeah. So
much variance?
basically, the story is going to be that this upper bound, of course, it's always true, but it's only sharp in low dimensions. Okay. And in high dimensions, all the clusters will actually be much smaller than this bound. And as a consequence, in some sense, it will lead there to be many, and for things to be concentrated, and so on. So let me explain where this specific exponent comes from. Suppose I have two blocks next to each other, and I have some cluster here, A, let's call it, and some cluster here, B. Okay? When I go to the next scale, I'm adding in some, you know, it's possible that A gets connected to B just by an edge, right? Now, each edge, if this has side length L to the n, right, each such edge is present with probability of order L to the minus D plus alpha. Right, that's the definition of the model. Okay, now how many edges are there? Well, it's the size of A times the size of B. Okay, so the significance of this D plus alpha over 2 bound is that if these clusters have size larger than that, then they're actually going to merge by an edge with high probability. If they have size of that order, they'll merge just in this simple way by a single edge with good probability. And if they're much smaller than that, then they're unlikely to directly merge with each other by the addition of a single edge. Okay? So you can think what this proposition is telling you is that at criticality, you never have a high probability of directly merging these two largest clusters in the neighboring boxes when you go to the next scale. You might have a good probability, and that turns out to exactly characterize the non-mean field regime. Okay. And in fact, the proof essentially follows by just an analysis of what I was telling you. So the idea is that if these clusters do start getting much larger than this, then they merge with high probability, and that will cause this this quantity to grow very rapidly as you proceed up to higher scales. It will sort of cascading. You get this a crisis, if you like, where it keeps just growing very fast. And the way that we'll encapsulate that is via a lemma. So it's convenient when you state this kind of lemma. Really what's going on is once this quantity starts getting too large, it's going to just grow in some very bad fashion. But conveniently, instead of really analyzing that, it's more convenient to get some lower bound that just inductively implies itself at the larger scale, because that's the simplest form to iterate. Okay, and the lemma is that there exists a constant L naught such that for all L larger than L naught, there exists a finite such that if, so this is going to be an implication, if mn squared is bigger than a over beta times this, it's just convenient to put the square on the left-hand side to get simpler formulas, then the same bound is true at this larger scale, n plus L. Okay. So this is capturing this cascading effect. You know, again, the idea is if things get too bad, if this quantity gets too big, it will remain big forever.
And with the same constant.
With the same constant, yeah, yeah.
And beta is fixed before L0?
Yeah, good question. I think that this quantity, if I remember correctly, I probably won't do the proof in such a detailed way that you'll see exactly this constant management business, but this denominator of beta should mean that you can pick A independently of beta. But basically, I've just put the beta dependence of the constant explicitly in the lemma.
L depends on L?
Yes. Yeah, this is, sorry about the complicated quantifier order here, but that's how it is. Yeah, you should think how I'll first fix some large scale L by which I want to proceed, and then I'll fix this constant A. Okay, so maybe let me first say why the lemma implies the proposition. Okay, well, the point is, and sorry, the proposition is hidden on the other board. It's that at criticality, you have this order L to the d plus alpha over 2n bound on Mn. The point is that it suffices to prove a bound for subcritical beta with a uniform constant, right? So the claim is that if beta, first I'll just fix one choice of L, at least L naught. The claim is that if beta is less than beta c, then Mn of beta is strictly less than A over beta L to the d plus alpha, set this square to me, for all n. Okay? And why is that? Well, suppose not. Well, if not, you know, the lemma says if this bound, if the other inequality ever holds at a single scale, then it holds at infinitely many scales. Right, I have, if I look at any scale of this form, right, if this is false for some n, then it's false for infinitely many n. Okay, but this is a contradiction because we have the sharpness of the phase transition. So we know that for subcritical percolation, the expected size of the cluster at the origin is finite, and in fact you have an exponential tail. And it's not hard to see that this is just inconsistent with this kind of power law growth. So in fact, for beta less than beta c, right, because the clusters have an exponential tail, you actually get that Mn of beta is big O of log at the volume, just by the usual union bound once you have an exponential tail. Okay. Now, of course, the thing about the sharpness of the phase transition, it gives you no control of the constants here. But that doesn't matter because you're saying, okay, if this fails at one specific scale, it actually has to fail at infinitely many scales, and eventually, whatever this enormous constant that might be here is, eventually you contradict it. Okay. That's clear? Okay. So what's the idea for the lemma? Okay. Well, the first thing is we're going to pick, let's say we go up by this large number of scales, small l. Okay. So we get, we get L to the d times small l copies of this box lambda n in lambda n plus l. Okay? Now I know just by the definition that each copy has a good probability to contain a cluster of size at least mn beta. Actually, because of these discretization effects, you have to put a -1 here, because maybe this probability drops from being close to 1 to close to 0 as you change by 1, but that's not a problem.
Just one question about the previous case. So before you showed that when beta is less than beta critical, so you.
Oh yeah, sorry.
But
I didn't complete the argument. Yeah. Then you just use a continuity measure. The point is, so you get that what you conclude is that this inequality holds for all beta less than beta c. But then you just take beta to beta c, right? The point is well, it does depend on beta, but in a way that doesn't blow up. In fact, it gets better as beta goes to beta c. Okay. So there's no problem just taking the limit.
Okay.
Right.
Even with the n and the uniformity in n, it's okay. You can work it out. Okay.
Yeah, I mean the point is that this quantity is just it's a finite box quantity. It's continuous.
Okay.
Okay. Well, actually, I guess there is this issue with it's the median, so maybe it's actually not continuous, but it's continuous up to adding 1 or subtracting 1. Okay. Good. So, and there's a similar issue here. I won't dwell too much on those off by 1 errors that you get when working with medians. That's just how it is. It's not going to be important for this proof. Okay. So let's fix. If we take L large enough, we can just use the weak law of large numbers, right? And say, well, I know that basically 1 over e of these are going to have so let's just say, by the weak law of large numbers, if I take small l large enough, then at least 1 over 100 of these copies contain such a cluster with probability at least, again, not really doing any optimal management of the constants here. Okay, this is just using the weak law of large numbers. Okay, all we're using here is that 1 over 100 is smaller than 1 over e. Okay. Okay, so you have on this very high probability event, you have that a good number of these guys contain some large cluster. Okay. So let's suppose that this implication holds, right? So large means at least, let's say a over 2 beta, just to put the 2 there to get rid of this -1, which is of course overkill, but it's slightly neater to write things that way. Okay, the square root of this. Okay, so you know, as I was saying, if I take two of these clusters, what's the probability they merge? Well, roughly, you multiply these two sizes together, and then you multiply by the probability of each particular edge being there, right? Now, of course, we've gone up a large number of scales, so those probabilities might be quite small. You know, it might be this cluster merging with this cluster, right? But the point is, what do each pair of large clusters, well, they merge with probability at least some constant times, you know, the product of their sizes, which is this A over 2 beta, L to the D plus alpha n, right? Times beta, actually, because, of course, that comes into the probability that you put an edge there, and that's why we put this factor 1 over beta here, it's to make these cancel, times L to the minus D plus alpha n plus L. Right, this is the edge probability. Okay, so what do you get? You get a constant times, you know, all the things with the n cancel here, right? You get an A, and you get an L to the minus D plus alpha small l. Okay, so of course, once you fix L, you can then take A large enough to make this large. Okay, now of course, this won't really be the probability if this is much larger than 1. It's a probability, but that just means the probability will be very close to 1 if this is much larger than 1. Right? It's essentially a probability that a Poisson is at least 1, and this is its expectation. Okay? So what you get if you take this constant A large enough after picking L is that any two of these points, large clusters, sorry, inside the n blocks, have a very high probability of merging when you go to scale n plus L. Okay? And as a consequence, well, this is now a Oda-Shreni random graph problem. But it's actually a really trivial Oda-Shreni random graph problem in the case that we very rarely think about, which is when p is very close to 1. Okay, so, you know, I'll say this is just an analysis of the random graph, but it's a really degenerate regime of the random graph. It's not any of the interesting, subtle things that you get near criticality or anything like that. I mean, you should think random graph with p very close to 1 means that if A is large, which you should think it means much larger than L to the D plus alpha small l, then all clusters, all the large clusters merge with probability, again, let's say at least 0.99. Just so in the end, we'll do a union bound over the bad events, and what we get will have, the bad event will have probability much smaller than 1 over E or 1 minus 1 over E or whatever it is, so it will give us a bound on the median. Okay, and now we're basically done. So, you know, this event that we've constructed, it has probability, you know, much higher than the threshold we need for the median. So, what we get is that under this assumption that Mn was large with a large constant A, right, we get that Mn plus L, well, it's at least the size of all these clusters that we merged together, right? So what was that? Well, we said that on our good event, there were going to be L to the D small l over 100 of these good blocks, good copies that had this large cluster, right? And then each one of them had size at least A over 2 beta L to the D plus alpha and the square root of this. Okay? And basically, the reason why we win is that the dependence on small l here is just it's a d rather than a d plus alpha over 2. So this is where we're going to use the fact, our assumption, actually maybe I didn't write this explicitly when I wrote down the proposition, but our assumption is this. Well, of course, actually, if alpha is bigger than d, it's again another situation where the bound we want to hold is just vacuously true because the cluster contains at most all the points of the box. But let's stick to this case. Okay. Okay, so the point is basically that we can take small l large enough, again, that we just using, if we write this as the thing we want, square root a over beta times l to the d plus alpha n plus l, right? Times, well, we get this root 2, and we get the 1 over 100, but then we also get the l to the remaining power of l, right? Which is well, it's d minus d plus alpha. Okay, so we can just take small l to be large enough that this is bigger than 1. Okay, so that's why you have to be a bit careful about the quantifier order in this proof. You say, I'll take small l large enough that this conclusion from the weak law of large numbers that I want it to be true holds, and this specific constant's bigger than 1. And you have to be careful, that when you define these constants, there was no circularity there, but it's fine. And then you take a large enough as a function of small l to make the other step work. Okay, and that's the proof. Okay. Is that clear? Yeah.
That seems to give you tons of room when alpha is strictly less than d.
Yeah, it does. I mean, again, the point is actually that really what's happening, if you wanted to do a finer analysis, and this might be relevant actually for the supercritical phase. Essentially what this proof is saying is once you exceed this bound on some scale, you actually know you're supercritical. And from that scale onwards, this mn is going to grow much faster than this power, right? It's convenient for an induction to just say that the bound reproves itself, but in fact, it's proving something much stronger. And in fact, what will happen is that, really once you exceed this bound, you're supercritical. So in fact, you're really growing like linearly in the size of the box from that point onwards. And of course, that's exactly what you see here. And you'll have some. I'm not sure this proof is a very good way of quantitatively actually analyzing that transition to supercriticality, but you could get some control of what's going on there by following this argument. Okay. So. Okay. So that's the proof of this bound on the this proposition. Yeah. Okay. So the next thing I want to talk about is what I call the universal tightness theorem. Okay. And this is it's a kind of a correlation inequality for percolation. It's actually just a consequence of the BK inequality. Which is going to let us go from having a bound on the median to having stronger estimates on means and second moments and even exponential moments. Okay, and this is something that I proved in my first paper on critical long-range percolation, which, as I mentioned, many of the methods in that paper are sort of obsolete now. But the key thing that was introduced there that is still really useful is this theorem. And I should say that this theorem is just about percolation on any graph, and it's also been very useful in some other contexts that don't have to do with analyzing critical behavior. So, for example, in my work with Philip on the qualitative properties of percolation on finite transitive graphs. We actually found many other very different kind of applications of this theorem. So what does it say? So suppose I have any weighted graph and some value beta. And suppose I have some set, some finite set. Okay, and I'll define k max of lambda to be the largest intersection of a cluster with lambda. Okay, so in particular, I'm allowing my clusters to live in the whole graph, and then I'm just intersecting with them with this set. Now, of course, in the proposition I was just telling you about, that's not what we're doing. We're saying just work within the subgraph. But of course, that's fine. You just change G. So you can do it either way. You can either be working in the big graph and just look at an intersection with the small set, or do things in the small set just by changing the graph. Okay, and I'm going to define Mn of beta to be the Edian of this quantity, exactly like before. So I won't write down the formula.
So, why did you choose Edian and not median?
Yeah, I regret doing that. It's mostly really the reason is, when you write your paper and if you're writing E to some complicated thing, you can also write X and not have the big complicated thing in the superscript. I mean, it looks much nicer. But there's no standard way of doing this with powers of 2. Oh, you can put some log 2s everywhere. That was essentially the reason why I did this. And in retrospect, I should have used the median because it's just the standard quantity. And OK, you can tolerate having some log 2s in your formula.
No, but I was just waiting for a super trick somewhere.
No, there's nothing significant about this. And you could use any other cutoff. I wouldn't be surprised. I mean, there probably is some optimal choice, and it wouldn't be surprising at all if it was 1 over E. But that optimization of the constants is certainly going to play no role in the in our kind of applications. Okay. So what is the universal tightness there? Okay, so the theorem is that essentially whatever graph you're working on and whatever subset you look at, this random variable is very well behaved in the following sense. So first of all, let's say you look at and I'll just write k max rather than k max lambda, and I'll write m rather than m lambda just to keep it simple. Suppose I try to exceed this by some constant factor. This is always bounded by e to the minus lambda over 9. Okay, so the point, the fact that this is 9 is inconsequential, but the point is it's a universal constant. Okay. If you want to be smaller than the median by a factor epsilon, it's bounded by 27 epsilon. Okay. And moreover, if you look at a specific vertex, and you ask, how likely it is that that specific vertex is in a cluster with large intersection with lambda, where large is still measured with respect to m, which is still the EDN of the largest cluster, not of this intersection. Then this is bounded by E times the probability that this intersection is larger than 1 times this threshold times e to the minus lambda over 9. I guess maybe I'll just write it like this. Okay. So again, a really key point here is that this, all these bounds, they just have universal constants in them. Okay.
Sorry, I'm lost with the notations here. What is Kn?
Oh, sorry, that says Ku. Which I mean the cluster of U. Where U is just some vertex.
I'm also a little bit lost. In fact, Mn of beta, what is N? So is an N?
Oh, yeah, sorry, there's no N. Sorry, I was reusing the notation from before. Yeah, it should be M beta lambda. Okay, so these first two parts are saying, you know, whatever this largest cluster is, it has this kind of exponential upper bound on its distribution, right? Like, you know, these are if you have an exponential random variable and you scale by its mean, these are exactly the kind of quantities you see. Okay, now in many situations, the truth is much better than this actually. You know, so actually, especially if you're working not at criticality, typically away from criticality, this will actually be concentrated. So, you know, it really has lives in some very small interval. This doesn't say that, and that's not always true. I mean, if you do actually critical percolation on the Erdős-Renyi random graph, for example, you'll really get a non-trivial limit law that's not concentrated for this largest cluster size. And in fact, I think in all known examples like that, you even get a power of lambda that's bigger than 1. You know, you even get a super it might even be lambda cubed in the Erdős-Renyi. Is that right? So in many situations, you actually have much better tail estimates than this. But the nice thing about this is that it's always true. And, you know, exponential tail estimates will certainly be good enough for everything we're doing. Okay.
And this is unrelated to the hierarchical lattice.
This is for any weighted graph with universal constants. Nothing to do with hierarchical, although we certainly will apply it in the hierarchical model. Okay. So so the first two things give you this sort of shape theorem for the distribution at the largest cluster size. The last thing says that if you look at a specific vertex, then once you try to go above this largest cluster size, it becomes very difficult to do that, and you start getting this exponential dampening. Okay, and as a corollary of this, if you happen to be working in some graph where you know in infinite volume that you have some polynomial tail estimate like this for the volume tail, then there exists a finite constant A such that for all lambda contained in V finite, the probability that you so K is now the cluster at the origin. This has a large intersection with lambda. It's bounded by A n to the minus 1 over delta, e to the minus n over 18 m beta c lambda. Okay, so in other words, if you also happen to know that in infinite volume you have this power law tail, then when you restrict to finite volume, you get the power law tail and an exponential term when you start going above this typical size of the largest cluster. Okay, and you know, the proof of this from this, it's just calculus. I mean, you just, of course, if n is just is smaller than m, then it's just trivially true. You just use this bound and change the constant to absorb whatever constant you had here. You know, if n is larger than m, you use this estimate and just say, okay, I can, by changing the constant in the exponential, changing it from 9 to 18, I can put this prefactor always, and it's just some simple analysis like that. Okay. Good. So, you know, this should remind you of back on a week ago. I was talking about these scaling and hyperscaling relations, and how the way you derive many of these scaling relations is that you assume a certain kind of ansatz formula for what the distribution of various things look like, either when you go away from criticality or you restrict to finite volume. And you should think that this looks very much like an inequality version of that, where the role of this typical large size of the cluster in the box is played by the edian of the maximum cluster size. Okay? Now, in the low-dimensional case, that's actually a completely sharp thing to do because the largest cluster is the right thing to look at. Okay? In high dimensions, the largest cluster will be, I think this is actually open to prove. There's an upper bound that Eisenman did in the 80s. I think the lower bound, the matching lower bound hasn't been shown, but the largest cluster should be larger than a typical large cluster by a log factor, basically, because there's polynomially many of these large clusters. Each one of them has something like a chi-squared distribution, probably. So the largest one will be it gets lucky and will be larger by a log factor. There should be some extreme value statistics and so on. So this is not quite the right quantity to look at in high dimensions. It's off by a log. And in the critical dimension, it should be off by a log. So, okay, depends whether you care about that. But it's always true. And again, you should think that this is almost sharp always for critical percolation, and it should be sharp actually in low dimensions. Okay. It's also sharp for high dimensional percolation, like on a torus. There are interesting differences there between the boxes and tori. They actually behave very differently in high dimensions. Okay. So another corollary is that under the same assumption, let's call this star, if this holds, the volume tail, then for any set, the edian of the largest cluster size is bounded by some constant times the size of the cluster to the delta over, the size of the set to the power delta over delta plus 1. Okay, and moreover, if you look at the average of the two-point function from some points to v, where v is summed over the set, then this is bounded by, again, up to some constant by the size of the set to the minus 2 over delta plus 1. Okay? And you know what you should think, if you take lambda to be a box, so you're looking at the average of the two-point function over a box, then this is giving you the relation between critical exponents 2 minus eta is less than d times delta minus 1 over delta plus 1. Okay? This is something I mentioned a couple of times before. The equality, this should be an equality in low dimensions. It's one of the hyperscaling relations. Okay? But what this is showing is an inequality in all dimensions. So if you want to formulate it this way, you have to assume the exponents are well defined and so on. But you know, this inequality just says, okay, if you have a power law upper bound on the volume tail, then you get a power law upper bound on the 2-point function, and it's equivalent to this if you assume that the dimensions are well defined. Okay, a corollary of this, by the way, is that you can't have eta equals these two mean field values of the exponents for nearest neighbor dimension strictly less than 6. So, going back to this original question, and this was I'm pretty sure already known via some less sharp bounds of the same flavor. But indeed, you can just check here that this does say you cannot have mean field critical behavior in less than 6 dimensions, at least in this version, where eta is 0 and delta is 2. Okay, so
so I'm a little lost about the strength of this theorem.
Yeah.
So you have a weighted graph.
Yeah.
The J's of course play a role in the. But here the weights play no role at all.
Yeah, well, they changed the distribution.
Yeah, but the bounds, 27, the 9, whatever.
Yeah.
Feel nothing of that.
They don't feel that. The thing is the cluster sizes are always defined by counting vertices. If you wanted to define the cluster volume in terms of some total weight of edges or something, then you would see that. But I'll show you the proof of this soon, and you'll see there's nothing mysterious happening here. Okay, but let me first say why this corollary follows. And essentially, the universal tightness theorem is letting us kind of implement some of these heuristic calculations we were doing with these ansatz formulas when we were talking about scaling theory right at the beginning, and just do that rigorously, at least in an inequality version. Okay, so for example, proof of corollary. Let's say you fix a vertex u and sum over lambda of the 2-point function. Of course, that's the same thing as saying take the expected size of the intersection, which is the same thing as summing the tails. Okay. Plug in the bound from the first corollary. N to the minus 1 over delta, e to the minus n over 18m. Okay, and then as I said, and of course, in this case it's completely explicit, so there's no problem justifying this. When you have a sum like this of something decaying polynomially times exponential with a very small constant, you basically sum to just the point where this exponent becomes 1, and you'll get up to constants, you'll get the right answer. That's not difficult to justify. So in this case, you'll get m to the 1 minus 1 over delta. Basically, you're just summing up to m, or 18m, or whatever, if you like, and you won't change the constant, which is, of course, the same as m to the delta minus 1 over delta. Okay? In particular, if I sum over both vertices, it's bounded by the size of lambda times this. Just trivial. Okay. Now, on the other hand, I can also lower bound the same quantity, right? So, this sum over two vertices. Well, of course, it's the same as the expectation of the sum over u and v of the indicator that u is connected to v. Right, which is the same as the sum over clusters of the size of the cluster squared, which is at least the contribution from the largest one. Which, up to some, the usual off by 1 nonsense with medians, it's bounded below by some constant times m squared. Okay? So all you have to do is just compare compare these two inequalities, that gives you an upper bound on M, which was the first claimed one in the corollary, right? This one. And then for the 2-point function upper bound, it's just already written. You just plug in the upper bound on M. Okay. Is that clear? Okay. So again, the point is that once you have this universal tightness theorem, and here we were really using that third part, right, about this cluster of a specific vertex.
I'm sorry, your 2-point function here, you wanted to sum on U and V.
No, I don't have to actually. I mean, I do that in the course of the proof, but I proved this bound first with only one of them summed over. Yeah. I think I pointed at the wrong place on the board when I explained it, but yeah. Okay. Good. Okay. Let me. Okay, so hopefully that was clear, the proof of the corollary, and convincing that this is a useful theorem. So now I want to briefly explain how you prove the universal tightness theorem. And I think this proof is actually it's quite easy. It's a purely combinatorial proof in some sense, and it can be used to prove many other similar statements about other quantities. For example, if you wanted to place the volume of the cluster by its capacity or something, if you have an increasing subadditive set function or something, you can run all the same analysis with the volume replaced by that. There's a lot of things you can do, slight variations on this that I think may be useful in the future. I haven't found uses for all of these things yet. I should say in my hierarchical paper, the later hierarchical paper on all the renormalization stuff, I proved and used a version of this where you replace the maximum, which you can think of as the L infinity norm of the cluster sizes, with the LP norm. And there's also a version of the universal tightness theorem with the LP norms of the cluster sizes. In the end, that wasn't useful. That was one of the things I had to not use to figure out how to do the ZD case, because it was much less useful there. But just my point is just that this proof has a lot of flexibility. You can use it to prove many other related things, and I think several of them will turn out to be useful. Okay, so what's the idea? Okay, so really the way we're going to prove this, so it suffices to prove that if I look at the probability that this largest cluster is at least 3 to the k times some quantity lambda, then it's bounded by the probability that you're at least lambda to the power 3 to the k minus 1 plus 1. And similarly, if I look at a specific vertex, again ku, with the same thing, I get a bound with one copy of this event and three to the k minus 1 copies of this event. Okay. Once you prove these inequalities, the theorem as I wrote it before is just an analytic consequence of this. Hopefully it's clear that once this becomes smaller than a half, if you're doing the median, or 1 over e, it means it has to decay exponentially above that. That's clear. And on the other hand, you can also use it to get the lower tail estimates, essentially because if if this wasn't close to 1 for lambda much smaller than the median, then by just applying the inequality from that value much smaller than the median to the median, you get a contradiction. Or if you don't have to phrase it that way, you just do some algebra. Okay. Good. So how is this proven? Well, it's proven via the BK inequality. And really, it just follows from a certain inclusion of sets, which is really that you just get that this event is contained in the disjoint occurrence of this many copies of itself. In other words, if I have a cluster of size at least 3 to k lambda, I can find I can find this many edge disjoint subgraphs of that cluster whose vertex sets, which are not necessarily disjoint, have size at least lambda. Okay, so this is a purely combinatorial fact. And for the second thing, it's exactly the same, but if you look at this event, then you get just 3 to k minus 1 copies of this event and 1 copy of this event. Okay, just because basically one of those subgraphs is going to contain. Yeah.
What the event here? What are these little dots?
Oh, the circle is the disjoint occurrence. Right, so it's the disjoint occurrence of A and B means you remember the definition of a witness for an event. It's just a set of edges that guarantees that the event holds. So this is that A and B both hold, and there are disjoint witnesses for both of them. So the dots in the middle are just saying that there are a lot more of these. And in other words, this is saying if you have this large cluster, then you can find many disjoint witnesses for the fact that you have some cluster smaller than that. Okay? And this is just a purely graph theoretic fact, right? And so really the combinatorial lemma, which I won't write down, just says if you have a graph and a distinguished set of vertices, which will correspond to our intersection of the cluster with lambda, then you can always take a large number of disjoint sets of edges, so that each set of edges spans a connected graph, which is of course a key point because they need to be connected in order to tell you that you have a large cluster. And these sets together cover the whole vertex set of the graph, and that each vertex should be adjacent to at least one of these edges. And each one of them, so really the way you prove it is just by, it's a divide and conquer, it's a recursive construction. So you just say that basically you can do this with k equals 1, right? That if you have a large graph, you can split it into 2 edge disjoint subgraphs, which each take about roughly half of the total graph. Okay, and the way you prove that is you just actually, you take a spanning tree first. You can do that without loss of generality. You can consider being on a tree. And then what you do is you basically want, and you have this distinguished set A, which is going to correspond to the intersection with lambda. So some of these vertices are special. And you want to form some these 2 edge disjoint connected subgraphs, which roughly split the vertices of A evenly. Now, of course, they can actually contain, if this edge is in one graph and this edge is in the other one, then they both contain this vertex. That's fine. So you want each of them, if you look at the vertices incident to that set of edges, it should contain between 1/3 and 2/3 of the edges of the vertices of this distinguished set A. Okay? And the way you do that is you just say, I'm going to grow one of the trees step by step, in such a way that I always preserve this property that it and its complement are connected. And at each step, I grow it in such a way that holds, and I add as little of A as possible. So for example, let's say you start with one of the trees is everything and the other tree is nothing, but you think of it as starting with this vertex, say. Okay? And now you always want to grow in such a way that you keep the complement connected, right? So basically you'd have, in this case, you have two choices. You either add this whole set in or this whole set in. And of course, the way to do it that includes as little of A as possible is just to add this edge in. Okay, maybe let me say, I'm going to add another vertex here. Okay, so the next step, okay, you have to add this edge. It's the only thing you can do. The next step, you have to add this edge. It's the only thing you can do. Now you have a choice again, and let me add this point, another point of A, just to make it an obvious choice. You have to add this whole branch or this whole branch again, because that's going to be what's going to preserve the complement being connected. And you'll pick this one because it has fewer points of A. And then you grow this, and then this, and then this. Okay. So this defines a process where one tree eats the other tree. Okay. And you just wait. Say, what is the first time the growing tree has at least a third of the vertices of A in it? And what you can prove, it's kind of obvious actually if you just think about it for a minute. At that first time you get at least a third of A, you don't have more than 2/3 of A, right? Because that just meant you made the wrong decision. You didn't pick the branch that had the fewest elements of A left in it. Okay, so that's the combinatorial lemma, and that's how you get these. So that tells you how to cut a cluster into two witnesses, and then you just recursively apply this over and over again. Okay. All right. Any questions on that? Okay. So that's the end of this digression into this universal tightness theorem. So let's now go back to our hierarchical percolation problem. So where we left things off is that we had proven the upper bound on this Edian cluster size. And what we now know, following this, is that this is actually a very useful quantity to have control of. Okay, so the next thing we want to do is the next goal is let's define Kn to be the cluster of the origin in this n block lambda n. So again, that means you're not allowed to leave the block when taking this cluster. Okay? And what we want to show is that at criticality, the expected size of this is at most some constant over beta c. This is not the same constant A as before, times alpha. Okay? All right, and you can see that this is, of course, very closely related to bounding the two-point function. I mean, it is bounding the two-point function, but the two-point function inside a box, right? Because these connections are not allowed to leave the box. Okay. And again, the strategy is going to be quite similar to before. We're going to have this, what I like to call a runaway observable argument. So we basically want to say, if I take A large enough, if this bound is ever exceeded at some scale, then it gets exceeded very badly at subsequent scales. Okay, and so the way we're going to do this precisely, the lemma, it's a bit simpler than the previous one, which is that the expectation on scale n+1 is at least some constant times, let me get rid of this factor of beta is needed if you're working at. Actually, we can just do everything directly at beta c here, so we'll just absorb the beta c factors into the constants. L to the minus alpha n times the square of the quantity at the previous scale. Okay, why does the lemma imply the proposition? Well, in fact, we don't even need to use sharpness to phase transition or anything like that. You can actually see if this bound is ever exceeded with a large enough value of a, basically so that one of these factors cancels this factor, you actually start growing doubly exponentially, right? It's like eventually this term completely overwhelms this one, and you're essentially squaring every time. And that's just impossible because this is at most the number of points in the box, which grows exponentially. Okay, so you don't need sharpness or anything like that to go from here to here. Okay. So, how are we going to do the lemma? So we'll take two blocks next to each other. There'll be more than that when you go up one scale. Of course, in general, there's L to the D, but we just need two of them. Okay, and let me call this lambda n and this lambda n prime. So they're two copies of the n block that are next to each other. And I'll take f to be the sigma algebra generated by the edges in one of these two boxes, in either of them, but not between them, is the point. So I want to understand what happens when I add the edges connecting these two things. Okay. Now, if I look at the expected size of the cluster at scale n+1, given what I know at scale n in both of these two boxes, okay? Well, one way I can include points is that I look at the points over here and I count how many points there are that are connected by this, in this scenario where there's a cluster here, and they're connected by a single edge from the cluster at the origin to here. Of course, you can also go back and forth and so on, but that's only going to help. Okay, so this is at least, and I'll take script C prime to be the clusters in lambda n prime. Okay. This is at least the sum over these clusters of their size, which is how much I win if I successfully connect to them, times the probability that I connect to them in this simple way, which is 1 minus, it's this Poisson probability, beta c, there's a constant here, times the kernel, times the size of the cluster at the origin, times the size of this cluster. Sorry, let me make some more space for myself. I'll rewrite that less messily. Right, it's e to the minus constant L to the minus d plus alpha n, size of the cluster at the origin in the box on the left, times the size of the cluster you're trying to connect to. Okay. Now, what we said before is that the maximum cluster size is bounded above by the square root of 1 over this. Okay. So what that means is that with high probability, all of these things that appear in the exponential are order 1. At most, they might be small. Okay. And what that means, but we have more than that. The universal tightness theorem tells you that you have exponential tails of going above that and so on. It really is not going to contribute to the expectation. Okay, so I won't show you all the details, but basically what you want to say is that when I take expectations here, the control of the tails I get from the universal tightness is good enough to linearize this exponential. Okay, at the cost of, this is not actually small necessarily, so you won't be able to say it's like exactly linear, but it will be bounded by a constant times the linear. Okay, you can do that. So this is where you use this bound and the universal tightness theorem in some not especially interesting way, so I'll spare you the details. You get, this is bounded by a constant times the expectation of the sum over these clusters of the square, where one power came from here and the other one came from here, times the size of the cluster at the origin, times the this edge probability. Okay. And now what I claim is that this bound here is actually equal to the claimed bound in the lemma. Okay. And the reason is that these two things are independent of each other, right? These two boxes. So I can factor out this expectation. That gives me one of these. And then if I look at the sum over squares, what you can notice is that, well, I could write this equivalently as the sum over all points in the other box of the size of the cluster, right? Because if I do that, each cluster gets counted by the number of points it contains, so you get the square. And of course, by symmetry, and this is where you slightly benefit in the hierarchical case, although this is not particularly important actually, you get that this is the size of the box, which is L to the dn times the expectation of k. Okay, and then if you just do the algebra, you see that this is the claim bound. Okay. Any questions? Okay.
It's not really an expectation because you have the conditioning that the maximum cluster is not too large.
Yeah, that's just the step I didn't explain properly. Yeah, this is when you go from here to here.
But that is not the exact result that you prove.
I do prove that. It just involves the step I didn't show you. That you don't condition. You say you use the fact that you have these good tail estimates to pass from here to here. That involves a few lines of calculus that I'm not showing. But the point is that you don't just know that the maximum cluster is not too large. It has very good tail estimates and so on, and this is enough to say, actually, the contribution, the error you get in the linearization and so on, you can handle it.
Okay.
Yeah, I mean, but basically, you don't condition. You put in some indicators. So really, the intermediate step, if you like, is to say the expectation of kn is of the same order if I add the indicator that it's not larger than some big constant times this because of the exponential tail, and then you can put in the indicators here. The inequality you get out here will include these indicators, but you know that doesn't change the order of the terms, so that's how it works. Okay. Good. So you can see, what we have here is we have essentially proven a two-point function estimate, right? But now what it is it's an average, but it's an average where we're really looking at this restricted two-point function, right? We're summing only over those points that can be connected to the origin inside the box. Okay? And what we would like is a global two-point function. Okay? And this is the step where we really benefit from working in the hierarchical case, actually. So in fact, at least if you formulate this in terms of the sum over 2 points rather than just one to deal with the lack of symmetry, everything we've done here works for ZD. There's no problem at all. And the thing is, like, the way these arguments work, they're always saying, you know, it's this runaway observable thing. If the quantity gets too large, you go to the next scale, you add in some edges, it gets worse. You know, and what happens in ZD is that, well, the Euclidean kernel is just larger than the hierarchical kernel, right? I mean, there are these points that are actually close to each other, and you have a much higher probability of adding an edge there. That only helps these arguments to work. It just helps this cascading effect to occur. So in fact, everything we've done up to this step, other than some uses of transitivity, which basically just mean you need to replace these quantities by the versions where you sum over 2 points instead of 1, everything works. And it's this last step that doesn't work at all, but it's very easy in the hierarchical case. So what you say, to finally prove the theorem in the hierarchical case, you say, okay, let's suppose I want to connect from the origin to X. Okay, well, I'll do a union bound over the scale at which I first become connected to X. Right, so let's say X is in lambda n and not lambda n minus 1. Okay, so one way I can be connected to X is in this first possible way where I might be connected to X. Otherwise, I'll take the sum of the probability that the origin is connected to X in scale n plus k plus 1 and not in scale n plus k. Okay, and of course this first quantity I already have a bound on, at least in average. I should say, one of the nice things in the hierarchical model is that if you use a kernel which is symmetric under all the symmetries of hierarchical space, then of course the 2-point function also is symmetric under all those symmetries, and that actually means that the averaged and point-wise quantities are essentially the same. I mean, they only the 2-point function only depends on the distance. Of course, in the box you do have different distances, but still it's very easy to convert between point-wise and averaged estimates in the hierarchical case. That's one of the advantages. Okay, so how do you bound this?
It's an equality, right? Just to be sure.
Oh, yeah, it is. Yeah, there's somehow yeah, indeed. Okay. So what's the idea? Well, you know, you say, I need to bound this probability, right, that I become connected for the first time at some scale. And how does that work? Well, the origin, you know, you have the origin and X in this small scale lambda n. And the path has to look something like this. I connect to some point. I'm basically going to decompose according to the first edge I use to leave this scale. Look something like that, and then I somehow come back to X, staying inside this next scale up. Okay, and basically, the thing that makes the hierarchical case nice is that when you leave this box, you have to use a long edge. There's no other way of leaving the box. Okay, so if you just then use the BK inequality, where you have you have some point here, you have this edge that has to be open, you have this other point here, and then this connection back to X, right? You can bound this term by the sum over U and V of the probability the origin is connected to U inside lambda n plus k, UV is open, and this should be a sum where U is in lambda n plus k, V is in lambda n plus k plus 1, not lambda n plus k. P, V is connected to X. Okay? And the point is that you know exactly what this is. It actually doesn't depend on u and v. So you can just factor it out. Right? It's just L to the minus d plus alpha m plus k plus 1. Or with some betas or whatever, but forget about that. You factor that out. And these sums over u and v, they're then exactly the quantities you have control of. They're the average of the two-point function over some box where you're restricting with the restricted two-point function for the same box. Right? Where here you're fixing x and summing of v and so on. Right? So what you get when you do this, when you just apply the bound and do the algebra, you get L to the minus d minus alpha m plus k. And because alpha is less than d, this just gives you a convergent geometric series when you sum over k, and then you're done. And that's it. Okay. So, as I said, everything up until this step actually worked just exactly the same proof for ZD. And this last argument doesn't work at all, basically for the reason that when you leave this box, you don't have to leave it via a long edge. You could leave it via a short edge, and then this might not be small. And you can't factor it out. So I won't say too much about how to extend this to ZD, because I only have half an hour, and I want to tell you about a couple of other things. But basically, the idea is you go back to the beginning, and you define everything in a different way, where basically instead of looking at clusters that have to stay inside the box, you allow yourself to use all the short edges that are not in that box, but not long ones. And if you do this in exactly the right way, you can still get the argument to work, except that when you get to this stage, you have some more complicated inequality that concerns this funny thing where you're allowed to, you're looking at the intersection with the box, but you're allowed to go outside the box as long as you don't use long edges. And then when you get to this last step, you only have to add in these long edges. And then you're exactly in the situation where you can run something like this argument again. And it's a kind of a mess, and it in some ways seems like a very ad hoc argument, but you can make it work.
It's in the same paper? No,
they're different papers, yeah. I first did it in the hierarchical case, and I think maybe 2 years later I had the idea how to do the extension to ZD. Okay, so that's all I want to say about this two-point function upper bound. Yeah?
Can you explain again the use of BK? Do you need the paths to be disjoint?
Yeah, these are disjoint. You have this path, this edge, this path. They're all disjoint. If they weren't, then this wouldn't be the first. You take one, the simple path from the origin to x, and then you decompose according to the first time you leave the intermediate size box. So there's three pieces of one simple path, so they're disjoint. Okay. So of course I didn't tell you anything about the lower bound. And actually, the lower bound in the hierarchical case is very easy. It's much easier than the upper bound. All it is that you say there's a general inequality, which is at criticality. If you look at if you have any set, and you sum over edges in the boundary of the set, the edge boundary, so these are like the edges coming out of the set, and you have the weights times beta c, and then you have the probability that the origin is connected to x inside S. For any set S containing the origin, this is at least 1. Unless I messed up exactly the right thing, there might be some exponential here, and then it will be slightly different, but it's certainly at least a positive constant. Okay, this is one of the key observations in this so-called phi-p of S argument of Domino-Copan and Tassion, which gives a much simpler proof of the sharpness to phase transition. Okay, now in the hierarchical case, you can just take S to be a box, And these J's are all small. Again, that's this key feature of the hierarchical. It's the ultramasticity. It's that you have to use a long edge to escape the box. And you just rearrange this inequality, and it gives you the matching lower bound on the two-point function. In fact, with this formulation, and for the lower bound, of course, it's stronger to have the restriction to the box. Okay? And what Baumler and Berger did is they realized that, okay, if you try to do that in ZD, it doesn't work. But it does work if you replace the box with a box of random radius. That has this, at least when alpha is less than 1, which is the condition that they need for their sharp lower bound on the two-point function. So you just apply the same thing. You take S to be a box, but then you also average over the choice of the box. And in the regime where alpha is less than 1, this gives you on ZD the sharp lower bound. Okay. So, yeah, so that's everything I want to say about the two-point function, well, almost everything. So in my remaining time, I want to say something about the new work on the low-dimensional case. Okay, so one interesting point about this proof that we just saw for the two-point function, of course it works across all these different regimes. Sometimes you're mean filled, sometimes you're not, which is what should happen because Sachs says there's no change in behavior at the two-point function as you pass through the upper critical dimension. On the other hand, sort of also the proof doesn't have the power to distinguish between these different regimes, if you like, because it never uses anything like that. It's it just doesn't come up. Okay, and if you want to start understanding this transition, well, of course, we've already proven a lot about the high-dimensional case. But let's say we want to just understand what's going on. Well, in this proof, we had this proposition, right, that the Edian cluster size on scale n is bounded by, well, let's go back to ZD. The corresponding bound on ZD, which is also true. And let me say, I'll move to working with R rather than this exponential scale. So at criticality, if you look at the box of radius R, you always have this upper bound, big O of R to the D plus alpha over 2. Remember, the significance of this was if the clusters have this size, then they have a good probability to directly merge when you go to the next scale. So this is saying they cannot have a high probability. They might have a good probability. Okay? Now, the argument shows you this about when you only have the connections inside the box, but in fact, once you have the two-point function upper bound, you can deduce the version where you're allowed to go outside the box and you just take the intersection. Okay? And the key idea is that whether or not this bound is sharp is exactly characterizing the low-dimensional regime, at least in the long-range relevant regime. Okay? And basically, what I show is that, so we call the key definition is what I call the hydrodynamic condition, which is that this quantity, let me just call this MR, is little o of this upper bound. Okay? The reason for this name is that it essentially, this condition ensures that this renormalization kind of thing where you're scaling and adding in these extra edges, that it's acting like a deterministic dynamical system in the limit, which is related to this theory of, not that theory is used at all, but just for the name, it's related to the theory of hydrodynamic limits of Markov chains. And in the hierarchical, and of course you can define it similarly in the hierarchical case with the different names for the parameters. In the hierarchical case,
You mean hydrodynamic limits like Kipnis-Zaradan, this type of thing? Or?
yeah, you know, when you have some Markov chain and it interacting particle system, it converges to a PDE, that kind. Just this idea of extracting something, deterministic dynamics from random.
Hydrodynamic limits, and you're saying it's not useful. I mean,
I'm not actually using that theory. It's just like for the name, it's saying it's a condition under which random dynamics become approximately deterministic in an appropriate limit. Okay. So in the hierarchical case, so I think, you know, when we were discussing last time and the time before about this renormalization group type analysis of all the moments and so on, it all worked by writing down these ODEs and finding conditions under which you could approximately simplify them, right, into these asymptotic versions that you could actually solve. And what happens in the hierarchical case is that, let me call this just hydro, is that the hydrodynamic condition implies that all errors in ODEs are negligible, implies everything else, you know, that we were doing before. In particular, min field with possible logs. Or really, just from this, with possible functions of slow variation that might be anything. Okay, basically, all this stuff we're doing with writing down these ODEs and saying asymptotically you can treat things like they're independent and factor them. This one condition, the hydrodynamic condition, is enough to control all of the errors that ever appear when you do that. And that's using the universal tightness theorem, right? So the point is, once you know this, you actually know that you're very, very unlikely to get to this size, and that's exactly the control that you need to bound all the errors, okay? Okay, so in particular, in the hierarchical case, what you can say is that, well, this actually shows that if D is smaller than 3 alpha, you can actually deduce that the hydrodynamic condition does not hold. Okay? And why is that? Well, if you can do all this analysis, one part of everything else that we saw last time is that the so this might be really confusing. Let me go back to the hierarchical notation. If you look at the second moment, right, it's one consequence of this is that it grows like the cube at the first moment, so L to the 3 alpha n, maybe plus some slowly varying, with some slowly varying errors. Okay? That was one of the consequences of this ODE analysis. Now, on the other hand, we can use the universal tightness theorem to give an upper bound on this, which is like mn times the first moment times a constant. Okay? And this is bounded by L to the times a constant, L to the alpha n plus d plus alpha over 2n. Okay? And you see actually when d is strictly less than 3 alpha, these two estimates are just, they're contradictory. So what this says is that you cannot have this hydrodynamic condition in low dimensions. Okay? And in fact, you know, what we prove is that the theorem in the hierarchical case is that the hydrodynamic condition holds if and only if d is greater than or equal to 3 alpha. So it holds, including at the critical dimension. Okay? But what you see is that, and it's very funny, I think, that the way you understand the low-dimensional case is basically by contradiction. It's like, the thing is, this upper bound always holds, right? And what you're showing is that if you actually dip significantly below that upper bound, then you can run all your high-dimensional analysis and you eventually get something false. So you actually, what this shows is that, sort of, is that in fact, in the low dimensional case, this really is of the order in the hierarchical notation. Okay. Now, of course, not being a little o of something is not the same as being of that order, because you could have oscillation. But if you run this argument more carefully, you can do everything in a boundedly many scales kind of way, and actually show this stronger pointwise conclusion about different scales. Okay, and this gives you an exponent, right? And what you can then show. Well, you're already in a very good shape in some sense, because you've computed exactly an exponent in the low dimensional regime. And this, by the way, the fact that this hydrodynamic condition does not hold is really telling you that your clusters in the low dimensional case, they really do not look at all like trees, right? Because every time you go up a scale, these two clusters, that they have a good probability to directly be merged by one edge, but also by like 10 edges, right? Because it's just Poisson with like mean bounded away from 0.
So again, the fact that in the high dimensional case, it's much smaller than R d plus alpha over 2. From that, you deduce that there are very many, and their size drop.
Yeah.
And you can quantify a little bit their size.
Exactly. Eventually, you can understand everything by doing all this ODE analysis that we were talking, the hierarchical version of that, if you like, that we were talking about last time. But it's exactly giving you that picture where in low dimensions you have order 1 big clusters on a scale that control all the interesting behavior. In high dimensions you have some power, many, and in the critical dimension you have logarithmically many. But although qualitatively it's quite similar whether you have log many or power many, the point is that it's divergent.
And maybe, so do you expect that when there is only one cluster, the fact that, MR is only a little part of the information, and there's more, I don't know, richness in the fluctuation, or with MR you really control?
In the low dimensional case, yeah, I mean, there should be some kind of limiting distribution. I should say this order 1 clusters thing, it's really like, for any epsilon, there's some constant depending on epsilon, many clusters that have size at least epsilon times this, and I guess there should be some exponent there. Actually, maybe I do compute that exponent dependent on epsilon. Actually, I have to check my paper again, but there's certainly many more things you would want to understand, and like scaling limits, for example, we don't currently know how to understand, or like the limiting distribution of either the largest cluster or often the size-biased cluster is the better thing to look at. These we don't understand. Okay. So this gives you this exponent, the largest cluster size, and what you can then show is that there really are versions of the hyperscaling relations that are true. And the precise formulation is that, okay, we know in the hierarchical case at criticality, this cluster inside the box, it grows like what would be R to the alpha in the ZD notation. And what the theorem that's the sort of rigorous hyperscaling theorem is that for all epsilon, there exists delta, such that if I restrict the cluster to be smaller than delta times this characteristic size, then it's at most epsilon. Okay, so this is kind of a technical theorem, but it's really giving you this hyperscaling thing, which is that the clusters which are not at this large scale, where there are order 1 things, they really do not contribute to anything you're interested in. The same thing is true with moments. Okay. And once you have this theorem, this is going to be totally unclear, but I've run out of time to explain it because I do want to say one more thing still. Once you have this thing, you can actually deduce the volume tail. So there's a sense in which this really is a rigorous version of this hyperscaling idea, and in fact, you can use it to prove the hyperscaling relation one-sided. But in fact, the other bound, actually we already knew because it follows from the two-point function plus these scaling inequalities that I wrote down earlier that are also a consequence of the universal tightness theorem. Okay, so in fact we get the volume tail. Okay. So I was talking so far about the hierarchical, but in fact, in the new work, what I'm able to do is to extend this analysis of the low-dimensional regime to ZD, except that we know that these exponents are not always going to take these values, right? So you'll remember last time I defined this assumption, the correlation condition for long edge relevancy, right? So this was essentially, in some precise version, that when you apply the cutoff at scale R, you make the model subcritical, you get a correlation length, and the correlation length condition for long edge relevancy was roughly that this correlation length is big O. It's the same order as the scale where you apply the cutoff. And essentially the idea is once you make this assumption, which again we know is true on ZD at least for alpha less than 1, you can, this just enables you to do redo the hierarchical analysis. In the hierarchical case, when you apply the cutoff, it's actually impossible to leave the ball of radius r, and this is somehow the main thing that is used that simplifies the hierarchical case. So if you just make an assumption that basically lets you redo that, then you can rerun the hierarchical analysis essentially. So in particular, what this leads to is that if d is less than 3 alpha and this long edge relevancy condition holds, which again is supposed to mean that you're in this, this regime, those two things together, then you indeed get that MR is of order r to d plus alpha over 2, and the volume tail is like n to the minus 1 over, oh sorry, I just wrote delta here, but of course I should have said with delta equal to the conjectured value, right? And also the two-point function. Okay. And again, the way this works, you also establish these hyperscaling type things. So just to say a little bit about how you prove this kind of hyperscaling, this rigorous version of the hyperscaling. Basically, what you do is you just apply, this trick that I keep using over and over again. You differentiate these quantities with respect to r. Okay, here it's n, but if you're doing it in ZD, you differentiate with respect to r. Actually, it's convenient to take, you go back to the first moment, and you take a minima with the threshold rather than putting an indicator there so that it's increasing function. And basically, I was saying that when you have the hydrodynamic condition, this is exactly what you need to make sure all these errors are small. But actually, if you just do this other thing where you just throw away the big clusters and then you look at the quantities that only depend on the small clusters, that also makes the errors small. And so, of course, it could just be that these quantities are really small, but if they have the correct order that they would have if you didn't have the threshold, and you have these asymptotic ODEs, then again, you can just do all the high-dimensional analysis again with these truncated quantities. And ultimately, you get false answers coming out, just the same as before. So again, the point is by adding in this thresholding, you can basically force that those ODEs to asymptotically simplify. Okay, so I'm sure that was a much too fast explanation, but there's one more thing I want to talk about, and I won't tell you any proofs of this, so it won't be too fast. So there's one additional thing that I realized, and this really relies on actually some new math that appeared not by me between the hierarchical and the Euclidean paper, and it can also be applied to do the same thing in the hierarchical case, which is to understand the k-point function up to constants in the low-dimensional regime. And I think this is really interesting, and it seems like there's many more things to be understood. So I'll go back to the tau notation. So this means the probability that these k points all belong to the same cluster. Okay, and I mentioned one bound we always have is the tree graph bound, right? Which is like it's this diagrammatic bound, right? Meaning that you sum over the midpoint and you have a copy of the two-point function for each edge. Okay. Now, this tree graph bound is the correct order in high dimensions, but it's not the correct order in low dimensions. As usual, in the critical dimensional, almost the correct order with some logs. So you can ask, well, what is the right way to understand k-point, like the three-point function, let's start with, in the low-dimensional case? Well, of course, it's something you can understand through these heuristic hyperscaling things again, right? So the point is, well, let me just say about the two-point function. If you have 2 points in low dimensions, in order for them to be connected, basically this guy should be in a typical large cluster at this scale. In this ball, this guy should be in a typical large cluster on this ball, where you just take the balls to be, of the order of the separation. And then if these hyperscaling type things are true, then they'll actually have a constant probability to be connected to each other given these two events, right? So this is like the square of this probability that just the origin is in a typical large cluster at this scale. Okay. What if you have 3 points? Well, of course, if they're like sort of equally, if all the distances are the same order, then you would get the cube. Okay, but of course, that might not be what your 3 points look like. It may be that these 2 points are quite close to each other and you get another one here. Right now, in that case, what's going to happen? Well, you pick one of these 2 points. It needs to get to this scale. This guy needs to get to this scale. But this guy only needs to get to this small scale, right? And it's reasonable to think if this guy is in a big cluster at this larger scale, it will also be in a big cluster at this small scale. And so what you can think is, well, first of all, when I went back to this version with 2 points, that means whatever this probability is, well, this is a bit silly, but it's the square of the square root. So in particular, if you have 3 points, it should be in low dimensions. It should be of the order the square root of the product of the 3 connection probabilities. Right, because the square root connection probability just is this one-arm kind of thing. Right? But you could also think in terms of just saying, okay, you figure out how to efficiently sort of route these points into each other, and then each one pays some one arm. Okay. Now, the really interesting theorem by Nikita Gladkov, who is a graduate student of Igor Pax at UCLA, and he's going to be a postdoc in Geneva in the autumn. is that for any graph, any weighted graph, and any 3 points, and any beta, the 3-point function is bounded by square root 8 times this same thing, the product of the three 2-point functions. Always. So this is really interesting. You can think that we now have two generic ways of bounding the 3-point function that always work. There's the Eisenman-Newman tree graph bound, and there's this Gadkov inequality. And they're both always true, but the Gadkov inequality is believed to be sharp in low dimensions, and the Eisenman-Newman inequality is believed to be sharp in high dimensions. And again, both of them will be slightly off in the critical dimension. Okay. So what this means is, for us in these low-dimensional models, once we understand the 2-point function, we actually understand the 3-point function, at least as an upper bound for free. And then using these hyperscaling kind of theorems that I was writing down before, we can also prove the matching lower bound, right? Because you basically just have to say, there's this explicit strategy that they can take to become connected, and I just have to check using what I know that it does really work. Okay. There's an annoying thing, which is that, actually we don't, in this regime, in general, we only know how to get average bounds on the 2-point function, and this doesn't play very well with that. But at least in this regime, alpha less than 1, so in particular in the whole one-dimensional case, then we have pointwise bounds on the 2-point function, and therefore pointwise upper bounds also on the 3-point function. And then by analyzing this strategy, you can get pointwise matching upper and lower bounds of the same order on both the 2-point function and the 3-point function. And in fact, you can do it for all the k-point functions. And I think that there's something super interesting here that I don't fully understand yet, whether it's actually useful or not. But okay, well, you can ask, what is the correct way of characterizing the k-point functions? Well, you can imagine there's a similar strategy, right? So basically, you have some cloud of points, and you want to decide how to choose. Each one is going to pick some scale to try to get to, and then it's going to be carried by another point up until you reach the top scale, right? So one way to think about that, you draw a directed spanning tree, just abstractly, on the points. Maybe it looks something like this. For each such directed spanning tree, you have an associated cost of trying to implement this strategy, where basically each point pays some one-arm probability. Again, for long-range models, you shouldn't really think in terms of one-arm events like connecting to a large distance, because the easiest way to do that is with a random long edge. It's not the right thing for these, but morally, it's a one-arm thing. And if you want to think about this in 2- or 3-dimensional nearest neighbor percolation, that is the right picture. So each one of these is paying a one-arm. And so each one has this distance associated to it in this tree. And if the 2-point is behaving like minus d plus alpha, each one of these one-arm things is like the square root of that. So it's minus d minus alpha over 2. You product over the points, where the root is just paying to go to the maximum scale. And then you have to maximize over the tree that you use. Okay? And this is indeed the upper bound, the correct scaling of the k-point function for these models that have hyperscaling. Now, the way we prove this is, again, for the lower bound, you just have to say, well, you pick this strategy and you just show that it works with the right probability. For the upper bound, what we use is a generalization of the Gadkov inequality to larger k-point functions. And the proof is exactly the same as his original proof, really. But the form is quite interesting. So let's say tau of A is the probability. It's not really anything about criticality, actually, so let's remove it. It's the probability that all the points in the set A are in the same cluster. So the generalization is that you get some constant depending on the size of A times the max over partitions. I'll call them tripartitions. So partitions of A into 3 non-empty sets of the three sets you get that are like the complements of each piece. Okay, this is, you can see in the case that A has 3 elements, this is exactly this. There's only one way to do the tripartition, which is into singletons, and you get the same inequality. Okay. Now, what is not at all obvious is that this is actually, if you do this recursively and you keep splitting down to 2-point functions, this is actually the same quantity as this, up to constants. It took me quite a long time to figure out. I was really hoping that it was just true, but it's not obvious. It's this kind of complicated combinatorial geometry thing. Again, they're not exactly the same. So in other words, if you know, you can define a quantity on sets in RD, where you take S of A to be the minimum over tripartitions of the square root of S. So you define it recursively via this relation with the initial condition that S of 2 points is the squared Euclidean distance. Okay, and it turns out that this quantity is equivalent up to constants that may depend on the size of the set to S of A to the minus d minus alpha over 2. Again, that's just a geometric fact. It's nothing to do with percolation. Okay, and so in fact, to get the upper bound of this form, it actually follows from this generalized version of the Gladkov inequality after recognizing these two quantities as the same. Oh, and I'm already over time, but let me just add one fascinating thing. This quantity S is conformally invariant. It's just exactly conformally. I mean, in the sense that if you apply Mobius transformations to A, this transforms in a simple way under Mobius transformations. And the reason that's true is because it's true for this Euclidean norm, and it just goes through the recursion. So this is what we've learned is that this model is conformally invariant up to constants. And of course, we allowed any norm. The norm, when we defined the model, could have been the L1, probably isn't rotationally invariant. But it is rotationally invariant up to constants. And, like I said, in physics, there's been a lot of progress made understanding the fact that actually Mobius invariance, even in 3 dimensions, is very powerful. And this has not really been investigated yet at all by probabilists, I think, as far as I know, in 3 dimensions. And here, well, we don't have conformal invariance, but we do have it up to constants, and it's very unclear to me whether this is going to be useful or not, but, well, I'm sure.
For the regime where D
is in the low, this is in this, yeah, in this regime. Yeah, you can also ask about the conformal invariance in the high dimensional regimes, and actually what happens if you define the higher k-point functions the way they tell you to in physics textbooks, the way you do the scaling means that actually the third one and up are just 0 in the limit in this regime. So actually the model is conformally invariant, but in some quite degenerate way, and it's basically saying it's Gaussian. Yeah, thank you.
There are questions?
Yeah. So usually, I mean, for higher, so beyond 2-point correlation,
yeah,
there's a natural notion of cumulance in probability.
Yeah.
There, I mean, they are also, it seems that, I mean, so in cumulance you subtract all sorts of, let's say, a pair of I mean, other lower degrees
Yeah.
of correlation. So it has this flavor, but it's not quite the same. So I don't know whether you.
Yeah, I don't have a very good answer, but I'll say, you know, if you want to do these similar kinds of things with the Ising model, then you definitely want to look at cumulants. But you know, actually, when you take those cumulants and then you interpret them with the random current representation, they look more like this kind of thing. So I think whether the exactly what thing is the appropriate object to say is your k-point function, it depends on the model you're studying.
Because in cumulants in particular, I mean, there's no such things as square roots. I mean, it's you wouldn't see.
Oh yeah, no, but you actually do expect to see. I mean, it's not. It doesn't. It's unclear this is really the right way to think of the inequality in some sense, but you will get this relationship for example, in 2 or 3 dimensional Ising. In fact, you know, if you look at a survey article on this 3D conformal field theory, they won't write it in this way. It will be in terms of the 3-point function is some power of the distances, but it's exactly the power that you get here. It's the product of the 3 distances and the powers of the square roots, or the exponents are half the exponents that you get for the 2-point function. So this is really something that's, in fact, in terms of the 3-point function, if you assume Mobius invariance, there's only one possible form of the 3-point function, and it's this, because of the way, you know, Mobius transformations act transitively almost on triples, right, up to some collinearity and issues and things like that. So actually, Mobius invariance basically, if you think in terms of this saying, you have these, it has to be a product of the 3 distances to the same power, and when you get to higher k-point functions, the Mobius invariance is no longer fixing exactly what's going on. Maybe I can add, even in the 3-point function, in the first order asymptotics, you should get some constant here, and this constant is like, well, I guess it's like the first structure constant of the conformal field theory or something, and that constant's actually very interesting. And in 2 dimensions, for nearest neighbor percolation, this was actually computed in recent work of Shin Sun and Morris Ang and some other people whose names are unfortunately escaping me right now, but this was a conjecture in physics by Delfino and Witt that there was an extremely complicated exact value for the leading constant in the 3-point function for nearest neighbor percolation involving all these special functions, the epsilon functions. And this was actually proven using all these Liouville quantum gravity techniques. Of course, we're very far away from that level of detail for these other models or in 3 dimensions.
Okay, so we should thank Tom again for his very nice lectures.
Thank you.